Welcome to my YouTube channel. Today is our lecture number 6 of linear algebra course. In the last lecture we described this set span of V1 up to Vp. Now we described this set in a bit more detail. So we note that span of V1 up to Vp contains every scalar multiple of V1 because scalar multiples of V1 are given by CV1, which can further be written as CV1 plus 0V2 plus 0Vp, and this is of course an element of this set. And similarly, scalar multiples of V2, V3 and Vp are elements of this set. In particular, the null vector can be written as 0V1 plus 0V2 plus 0Vp, hence null vector is also an element of this set. Now we provide a geometric description of span of a single vector and span of two vectors in R3. So if V is a non-zero vector in R3, then span of V is the set of all scalar multiples of V, because we know that span of V will be given by C times V, where C is a scalar, which is indeed the set of points on the line in R3 through vector V, and origin is described here. This is my vector V in R3. If I multiply this V with C, so CV will be all these vectors. Hence, in R3, the span of V is the set of all scalar multiples of V, which geometrically is the set of points on the line in R3 through V and 0. Similarly, if we have two non-zero vectors U and V in R3, and V is not a scalar multiple of U, then span of UV is the plane in R3 that contains U, V and the origin. It can be described geometrically as follows. This is my vector U, this is my vector V. So if I scalarly multiply V with C1, then they are given by these points. And similarly, scalar multiples of U2 are given by these. Now for any fixed value of C1, for example, if this is my C1V, and if I vary C2U for all C2, then I have all these points covered. And hence, in particular, span of UV contains the line NR3 through U and 0. This is, if I take span of UV, then it contains the line through U and the origin, and the line through V and the origin. So this is the line through V and the origin, and this plane basically describes the span of UV. Now we move towards some examples. So let A1 be this vector, A2 be this vector, and B be this vector. Then span of A1 and A2 is a plane in R3. The question is this vector in that plane? So we know that span of A1, A2 is given by x1, A1 plus x2, A2, with x1 and x2 be real numbers. So now for B, if we want to prove that B is in the span of A1 and A2, it is equivalent to show that B can be written as x1, A1 plus x2, A2. And if B is in this set, then this system must have a solution. Now, if I take the augmented matrix of this system, it is 1, minus 2, 3, this vector and this vector B, and which can be reduced to an echelon form matrix as this one. And now in this matrix, we know that rank of A is 2 and rank of AB is 3, and hence the system is inconsistent. It means that this system has no solution. It means that B cannot be written as a linear combination of A1 and A2, and hence B is not in the span of A1, A2. Another example, that let A1, A2, A3 be these three vectors, and let B be this vector, and let W be the span of A1, A2, A3, which can be described as x1, A1 plus x2, A2 plus x3a3. Now there are two questions basically, that is B in this set W, and show that a3 is in W. Now to show that B is in W, we look for the solution of the system x1 a1 plus x2 a2 plus x3 a3 equals B, and we proceed as in the previous example. If this system has a solution, we will say that B is in W, and if this system has no solution, then we will say that B is not in W. To show that A3 is in W, we know that W has this form. It is equal to x1 a1 plus x2 a2 plus x3 a3. Now in particular, A3 can be written as 0 a1 plus 0 a2 plus 1 a3, and of course this right hand side is an element of W, and hence A3 is an element of W, thus A3 is in W. The next example is that we have two vectors in plane, 2 minus 1 and 2 1, and B be a vector given as h and k. Now we show that B is in the span of uv for all values of h and k. So now we know that span of uv is equal to x1u plus x2v. For B belonging to the span of uv, we must check that the system x1u plus x2v equals B has a solution or not. The augmented matrix of this system is given by u, v and B, which is this matrix, and this can be reduced to this form. And now we know that the rank of AB is equal to rank of A, and hence this system is consistent irrespective of any values of h and k. Hence the vector B is in the span of uv for all values of h and k. Now we give a brief description of matrix equations Ax equals B. So if A is an m cross n matrix with columns a1, a2 and an, and if I take a vector from Rn, then the product of A and X denoted by X is the linear combination of the columns of A using the corresponding entries in X as weights of the linear combination. That is, Ax can be written as A1, this is a column, A2, this is another column, An, this is the last column, times x1 up to xn. This can be written as x1 a1 plus x2 a2 plus xn an, and from this part we see that this is a linear combination of a1, a2 up to an with weights x1, x2 up to xn. And hence in this matrix equation, the entries of this vector x can be considered as weights. For example, if I have this matrix A and this is my matrix X or vector X, this can be written as, this product can be written as 4 times 1 0 plus 3 times 2 minus 5 plus 7 times minus 1 3, which can be simplified to 3 6. And now in this linear combination, we note that the weights in this linear combination are 4, 3 and 7, which are exactly the entries of this vector X. So for V1, we have another example. For V1, V2, V3 in Rm, write the linear combination 3V1 minus 5V2 plus 7V3 as a matrix product. So in the linear combination, we know that 3 minus 5 and 7 would be the weights to form the vector X, that is 3V1 minus 5V2 plus 7V3 will be equal to V1, the first column, V2 will be my second column, V3 will be my third column, and the weights which form the entries of vector X are 3, minus 5 and 7, and hence I have this matrix equation, a matrix form AX. Now we consider a very simple system, x1 plus 2x2 minus x3 equals 4, minus 5x2 plus 3x3 equals 1. This system is equivalent to x1 times 1 0 plus x2 times 2 minus 5 plus x3 times 1 3 equals 4 1. We call this as a vector equation, and which can further be written as 1 0 2 minus 5 1 3 times x1 x2 x3 equals 4 1. And now this is in Ax equals B form, and we call this 3 as a matrix equation. So thus the equations in this system has the matrix form Ax equals B. Such an equation is called a matrix equation to distinguish it from a vector equation such as in 2. This is a vector equation, and we have a relation between these three. This can be considered as a linear combination or a vector equation. This is a system of linear equation. This is a matrix equation. So we have a theorem. If A is an m cross n matrix with columns a1, a2 up to n, and if B is a vector in Rm, the matrix equation Ax equals B has the same solution set as the vector equation x1 a1 plus x2 a2 plus xn an equals B, which in turn has the same solution set as the system of linear equations whose augmented matrix is given by this thing. That's it for today. Thanks.